Hi, everyone. Welcome back. So we're going to jump into week 7 in our lab module 3. So just to give a brief summary of what we're going to do today, we're going to briefly review what are the important material science concepts in the iron-carbon system, which is the material we're going to study here. And we'll talk a little bit about time temperature transformation diagrams, because these are going to be helpful for figuring out how to form different microstructures in this material. And then, of course, we're also going to design our experiment, think about what variables we're going to explore, and then also the data that's going to come out of this. Okay, so the first thing to do is remind ourselves what the iron-carbon phase diagram looks like. And again, this is very important because this is what represents steels. So what I'm showing here is a phase diagram with temperature and composition. It's heavily on the iron-rich side. So it's showing pure iron on the left side, and then iron with a few percent, so in this case, 6.7% weight percent carbon. Now, one thing to point out is that weight percent and atomic percent are not the same and often can be very different. And this is a good example. So carbon is relatively light. So only 6.7 weight percent gives you this ordered iron-3 carbon phase called cementite, okay? So that means that that is 25% carbon. Right? So that 6.3 weight percent becomes 25 atomic percent. In any case, we can see a few different transitions on here. We can have a eutectic transformation from the liquid down into 2 solid phases. We can also have a eutectoid transformation. So this is from 1 solid phase to 2 different solid phases. And that second thing is what we're going to sort of focus on in this experiment. We're going to start with this austenite structure. So this is a face-centered cubic structure. And we're going to cool down and come into this new 2-phase region. In this new 2-phase region, we're going to transform to what's shown here as alpha. So this is something called ferrite. So this is a body-centered cubic iron-rich phase. And it will also form that intermetallic composition, that cementite composition, that very ordered stoichiometry, right? And the combination of these two is something called pearlite. Now I'll explain that in a little bit more here. Okay, so we're going to look at some solid phase transformations. This is just showing a zoomed view of this type of transition, and it's showing what would happen if you cool down right at that eutectoid composition from the single solid phase regime to the 2-phase solid phase regime. And what you'll notice is that something interesting happens here. So we're going to go from a single phase of a intermediate composition, and we're going to want to decompose into a phase that is really low in carbon and a phase that is really high in carbon. Now, because that happens, what you actually get is this layered type of structure in your material. So locally, you want to go from some middle composition to 2 very different compositions. And the way you can do that is to form the stripe pattern. So locally, carbon is going to diffuse away from some regions towards others. Where it collects is going to be your cementite. And where it's lean or low in that carbon is going to be where the ferrite forms. So we formed this sort of striped pattern. Now, that's what happens at exactly that eutectoid composition. If you're slightly above or below, you can get a little bit of a modification to that. I'm just showing you these 2 options. So if we're just below that eutectoid composition, as we cool down, we would start to form some combination of the FCC phase plus a little bit of the BCC phase. The BCC phase is shown as orange here. And then whatever is left of that FCC phase, that austenite, once we go below that eutectoid temperature, that's going to transform into pearlite. Okay, so you get a very similar type of microstructure, pearlite plus that what's called primary or pro-eutectoid ferrite. If you're on the right side of that eutectoid composition, you get a different version of this. As you cool down, you start to form some of that cementite first. So this is the blue phase. And then whatever is left of that austenite transforms to the pearlite. So again, very similar. You get pearlite in there, but there's some primary cementite in the structure, okay? The key thing to point out is that all of these nuances about how it forms this layered pattern, sort of how it's arranged in space, is stuff that we don't get from the phase diagram, right? The phase diagram just tells me what phases are in equilibrium, what's the composition of those phases, and how much I have in the system total. It doesn't tell me these details of how they're arranged. So we're going to start to understand and see where some of those kinetics come in and how we can describe that today. So first thing we need to mention is how do we nucleate these new phases? Traditionally, people describe this in terms of a solid coming from a liquid, but that's not all that important. The idea still persists and is the same if we think about new solid phases coming from other solid phases. You still have this two-step process that needs to happen. You need to have local atomic fluctuations that nucleate your clusters or your new phases. And then these clusters need to grow and coarsen. Okay? You can describe what's happening as a function of the rate at which these things can occur. So this plot looks scary, but let's take it one piece at a time. So the red curve right here, this is showing the nucleation rate. So how quickly can we nucleate that phase that's now preferred based on the temperature that we are at? And it turns out that there is a peak in that rate, okay? So this peak value, so that means it's the rate it's the temperature at which this nucleation is happening the fastest, is a balance of you have enough driving force for the nucleation of the new phase, but you also have enough energy for that critical size nucleus to form that can then grow, okay? Just to contrast that, if I go at this high temperature, just below the transition temperature, I have lots of energy. So once I form these clusters, they can start to get big enough that they're that critical size. But there's a really small driving force because I'm just a little bit below the transition temperature. In contrast, if I'm super low in temperature, I have a huge driving force, but not much thermal energy. Okay, so it's the balance of those two things that gives us this peak. You can also plot, once you form a critical size nucleus, how fast can that grow and just take up pure volume of your material? And that generally is going to get higher as you increase the temperature, right? The overall effect is this blue curve, okay? So there's this little nose on the curve. So there's some optimal temperature where the transformation rate is highest. It's not the highest temperature, it's not the lowest temperature, it's some intermediate temperature. We often don't really look at these transformations as and sort of understand them in terms of the transformation rate. We actually usually take the inverse of that. So if I took this curve and I flipped it, what I would get is the temperature versus the time necessary for a given transformation. And this is what we call a time temperature transformation diagram. And any curve on a plot like this is going to tell us what's the time when that transformation is a certain percent complete, right? So let's look at what this appears like for our iron carbon system that we're going to study. So I'm going to show you, in this case, it's at the eutectoid composition. You could think about beginning at a temperature above that eutectoid temperature. So we're in that single phase FCC structure. If we rapidly cool and then let our sample sit and keep an eye on its structure, we would see some transition. At first, nothing would happen. It would stay in that austenite structure, even though it doesn't want to be there, okay? And that tells us that, again, the phase diagram isn't immediate. You need to have some kinetics happen. As we start to hit this first curve, so this is what we would call a 0% perlite. This is where the transformation starts. We would begin to see some changes happening. As we move inside of this curve, we could see that, and as we move to the right, more and more of my, in this case, it's sort of a light blue austenite, is transforming to this white and black striped perlite, okay? And as I keep going to the right, which means I'm letting it sit there for longer and longer times, I get more and more of that perlite until eventually that transformation is complete and my material is fully that perlite that the phase diagram tells me it wants to be, okay? At this point, we've hit the other side of this time temperature transformation curve. This is when the 100% of the transformation has happened, okay? And you can again notice some of those things like, well, at higher temperatures, it actually takes longer for this transformation to occur. So that's where we can see some of those things we just talked about in the last slide. It's important to talk about a few of the other options that the system has. So perlite is that descriptive word we use to describe these very finely spaced stripes of the ferrite plus cementite. If we cool down to a lower temperature, so this is on, if you think of this as the nose of the curve, this is below that nose of the curve. And we let the thing sit at that temperature, let the transformation occur, we form what is called bainite, okay? That's shown here on the right. It's sort of blocky chunks. So rather than finely spaced layers, it's these big blocks of cementite ferrite. What you'll sort of notice is that this organization of the two phases looks different. But since we would be at the same place on the phase diagram, we would end up getting the same thing, some certain amount of ferrite, some certain amount of cementite. The difference is how it's organized inside the material. Okay, again, that isn't shown to us by the phase diagram. I chose iron carbon because there's also another sort of wacky and cool example of something that can happen. So if this curve right here tells us when that transformation starts to happen, we can, in theory, cool down so fast that we miss that nose completely and we never let that transformation occur. So it wants to become ferrite and cementite, but we don't let it. Okay? And if we do that and we get to a low enough temperature, the system really is unhappy as a face-centered cubic structure and it wants to transform. And if it doesn't have the energy to become that those equilibrium phases, what it does is it forms something called martensite. Martensite is kind of cool because it's what's called a body-centered tetragonal structure. So it has a little bit of the feature of that ferrite that is in equilibrium at low temperatures, but it's not quite the same. So it's body-centered, so there's atoms at the corner. This is this blue rectangular prism, and then one at the middle, but it's stretched in the vertical direction with respect to the in-plane directions in this picture. So it's not a cube, it's actually a stretched out rectangular prism, okay? And the reason this happens is it's actually a transformation which can happen without diffusion. So normally to go from a face-centered cubic to a body-centered cubic structure, you need to have atoms diffusing around, which is why you need this thermal energy in that elevated temperature. Face-centered cubic can go to body-centered cubic just by having some elongation of the atoms. So it doesn't require diffusion. And you end up getting a different type of structure. And this is shown here on the right. You get some retained austenite. So some FCC structure is retained. And then you get all these regions that are shown as black in this picture. These are needles or little sections where that martensite is formed. Okay, so it's not on the phase diagram at all, but we can form this different structure. So let's think about how we're going to do this in our experiment. We're going to target 3 different microstructures to see some of the cool workings of time temperature transformation diagrams. The first thing we're going to do is we're going to pick a situation where we should expect to get perlite. Okay, so we're going to rapidly cool to some high temperature. We're going to let it sit there, let that transformation occur, and we'll get perlite and we'll see what it looks like and what its properties are. We're also going to try to get a martensite structure. So to do that, we're going to very rapidly quench from a high temperature, totally miss that transition, and get a material that has this martensite structure. The third sample we're going to do is we're going to take one that has been quenched and has martensite and see if we can modify it, sort of be away from this curve. So what we can do is let it sit for a while, and then we can heat up to some intermediate temperature, allow that to sit there and see how that affects the microstructure that we have. This is actually something called tempered martensite. So you start with martensite, but you do a tempering treatment. That just means an intermediate temperature annealing, okay? So we're trying to avoid all these transitions, but we will be trying to coarse in and evolve the microstructure kind of in a way that was similar to what we did in lab module 2, where we evolved those precipitates. Okay. So I had to go choose a material, and what I wanted to do was get something that is representative of just sort of general steel behavior. So I again went to McMaster-Carr and I bought some metal bars of what's called 1045 carbon steel. So its composition is primarily iron. It has a little bit of carbon. It's about 0.43 to 0.5 weight percent. It has a little bit of manganese and a little bit of silicon. And then it can sometimes have really tiny amounts of phosphorus and sulfur, okay? For our purposes, what we can really do is think of this as it's primarily iron carbon, some minor amount of manganese addition, and a few minor impurity elements too. Okay? So our next thing to do is orient ourselves on that iron carbon phase diagram now with our real material. So we can take that range of the carbon content. So we said it was 0.43 to 0.5 weight percent. So this is down towards the left side of this curve, and it's below the eutectoid composition. That was 0.73, okay? So what we want to do is that can inform where we are and what we would expect. If we cool this down, we would expect to get some primary ferrite and then some pearlite. It also gives us an idea of what temperature we're going to want to solutionize our samples before we do this quenching type of experiment. In the last lab module, we solutionized in the solid solution regime because we wanted to get just aluminum with copper on substitutional sites. In this case, we want to get our material to be fully that face-centered cubic austenite, so then we can see how that changes. So what we'll do is we're going to make sure that we heat above this temperature. We don't know exactly where we are in the composition space, right? The supplier gave us some range, 0.43 to 0.5. So what I'm going to do is just make sure I'm above this maximum liquidus temperature for this mixture, which is 912 Celsius. So to create that single phase austenite, what we're going to do is we're going to take our samples. We're going to have 3 samples, right? And we're going to heat treat them at 925 degrees Celsius. We'll take one and we'll rapidly cool it down, but let it sit at 650 degrees Celsius, where we'll form our pearlite. Okay? And just to go back and remind us, that's somewhere below that transition temperature or below that eutectoid temperature. Okay? We'll take another 2 samples, we'll quench them down rapidly to form martensite. One of them, we'll just take it away and we'll study that. And the other one, we will heat it up and let it sit there to make this tempered martensite. And I chose 500 degrees C to give it enough energy to coarsen and hopefully change the microstructure and the properties. Now, that tells us the temperatures that we're going to apply. The other thing we need to do is pick out the times, all right? So one issue is that we're not working with completely pure iron carbon, okay? So on the left was that time temperature transformation diagram that I showed you before. It's the same thing we saw before. On the right is one for, it's a different type of steel. It's not the exact type of steel we're looking at. It's a 4340 steel, which has some manganese, some silicon, but also some chromium, nickel, and some molybdenum. And what you can find is that a lot of the same features are there. So in this case, they have this transition from austenite to pearlite. You can see that same thing. You get austenite to pearlite. There's some retained ferrite because of the composition that they're at. But the main thing is all of those alloying additions, they end up slowing that reaction, that transition type of phase. So if you want to think about it, you can look at this curve on the left here and imagine they pushed the nose of that to the right. So they pushed it in and slowed that transition down. And instead, they see these 2 other types of peaks that are popping out. But more importantly, the x-axis values have changed. So if I look for right at that 650 degrees C, right after that transition to the pearlite has finished, I find very different values. So it only took about 2 minutes in that pure iron carbon system to have that pearlite transformation. But it says that it would take about 2 hours to have that transition in this 4340 steel. Okay, so that informs us. And what it tells us is that we want to do more towards the high times on the annealing treatments. So we want to make sure that the transition happens. So we're going to pick something a little bit longer. So I'll come back to those curves I drew. So I'm going to do that single phase creation for 3 hours, let's say. I'm going to hold that sample at the pearlite transition temperature for 3 hours. The way I did that thought process in my mind, that other example I looked at for the 4340 steel, it has even more dopants and should slow the transition more than my system. So it should be less than 2 hours, but I'm just going to give it extra time to make sure that this transition happens. Okay. And in terms of tempering that martensite, I'm going to let it sit there for about 6 hours. There's no exact sort of fundamental reason I chose that value. My thought process here was, if I'm going to anneal this one for 3 hours, I want to anneal it for a similar amount of time, but it's at a lower temperature, so I'm going to let it sit there longer. Okay, so I want to give it enough time, of course. All right, so the last pieces of this are, I need to look at it at room temperature and investigate it so I can quench these things down. That shouldn't be a problem because I've already let the transitions happen that want to occur. All right, so the last thing to talk about is, what is the data that I'm going to extract? So I'm going to have these 3 samples. They should have 3 different microstructures, even though they're at the same point in the phase diagram, right? They're going to be at same composition, room temperature on average. I'm going to go in and look at what's the hardness data from each of these samples. And what I'll be able to do is understand how their mechanical properties change just from different cooling treatments and where they are on that TTT diagram. But we're also going to go in and get images of the microstructure. So what we're going to do is get a very well-polished surface. We're actually going to etch away the surface and try to see some of those different features and try to make sense of what's happening on that surface, what our hardness values are, and how our material performs. All right, so we're at the end of today. Again, you have the background of what you need to start to introduce this lab module. What I will do next week, and we'll post a video of, is I'm going to take and prepare those 3 samples with polishing that we're going to use, and I'm going to do those heat treatments so that we have our 3 different microstructures that vary in important ways. All right, so I will see you all at one of our working sessions, hopefully, and have a good rest of your week.